Hello, this is about the transformer model. We are going to cover the functions and some components of transformer. There is an encoder and decoder, and self-attention, and positional encoding, and add and known. And we are going to discuss the decoder and the final layer. Okay. So, as you know, Transformer, there's a movie and toy and cartoon characters. It's very well known, but what you're talking about today is different from these Transformers. We're talking about basically the architecture, the deep neural network architecture that is very popular in NLP and now also very popular in computer vision and other fields. So the idea is from the attention model. So in order to improve the efficiency, we want parallelism, how we parallelize more of our processing steps. And so far, the RNN is more like a sequential procedure. So even if we have GRU and LSTM structures for RNN, for long sequences, we need attention mechanism. So the question is, if the attention can look at any state information, then probably, because we can look back to any past state, so maybe we don't need RNN, we just need attention. That was the idea of the transformer model when the model was created by the group of people. So this was published in 2017, and the name of the title of the paper is "Attention is All You Need," published by Google folks, and it got a lot of attention from natural language processing. The application they use for showing the effectiveness was based on machine translation, but it turns out the techniques can be useful for any NLP, many NLP tasks. And it became just de facto standard for many different NLP applications. And as I mentioned, other deep learning applications, including computer vision. And instead of the standard RNN, encoder-decoder model or sequence-to-sequence model, this focus on only use of attention. And not just one type of attention, it would use multi-head self-attention. Multi-head allows some parallelism, and through this we can reduce the time. That means the parallelism allows us to reduce, improve the efficiency. And compared to standard RNN, it can model long dependencies, like the tokens that are far from each other. And for optimization, the paper introduced layer normalization. and residual connection. And also for input embedding, in order to represent the positions of individual tokens, the positional encoding was introduced. And according to the paper, at the time, the machine translation, it reached top performance and also showed good performance for constituency parsing. And the codes are available in TensorFlow and PyTorch. That if you look for those packages, you can make use of the existing code. This is the basic model architecture shown in the paper. There is the encoding part on the left-hand side and decoder part. And there is an n times of this encoder stack can be multiple of this. So stack 1, 2, 3, the same structure. Could in the paper they use 6 of this encoding stack and then 6 of the decoder stacks. And we'll look at those stacks in the following slide. And in the attention computation, there's a query key value computation. This is something we look in the attention, basic attention mechanism. And also, this is not only one attention, it could be for the same input, there will be multiple way to look at the attention. It's called multi-head attention. So we'll look at this. The encoder and decoder. The encoder block, as I mentioned, there will be multiple of this same structure, right? Multiple times, 6 times. There's a self-attention layer followed by feed-forward neural network. So this 6 let's say I just explicitly show the 6 blocks. They have these 2 layers each, right? And then they have same structure, 1, 2, 3, 4, 5, 6, but that they will have a different parameters for each different layer. So encoder module has 2 layers again, self-attention layer and then feed-forward neural network layer. It's just basically feed-forward neural network is like an standard multi-layer perceptron. And self-attention is looking at the relation between the words in the same input sequence. So in the sequence-to-sequence model or encoder-decoder model, the attention was more like encoding part and decoding part. The decoder was looking at the tokens in the encoder part. That was the sequence-to-sequence model or encoder-decoder model. Here, self-attention means that within the same encoding sequence, there will be multiple tokens, right? And they are looking at the relations between tokens, right? So from each other, all possible combinations. And in the decoder module, this stack has self-attention and feed-forward, but also there is a encoder-decoder attention because the decoder part should look at the encoding, right? So when it generates the tokens or generate the output, we should look at what is currently generating but also in the input sequence. So that's encoder decoder attention. So for getting the inputs to the encoder block, we'll have an embedding of the individual token or individual word. So if this is French, je suis étudiant, for each position, there will be one token, and the token goes through their own path. The word has its own path in the encoding part. And here in this case, the length of the input will be 3, and the individual, but in the transformer, the number of tokens or number of words in the input will be 512 or 24 or something like that. This is very simple, just for illustrating the idea. So as I mentioned, when I mentioned the individual token is going through their own path, so here there's only 2 tokens in input, just to illustrate the idea. This thinking is embedding in the original token could be one-hot encoding, but it's embedded into if this is embed using the word2vec, maybe you'll use 512 vector, size of 512. The original one-hot encoding, the size will be 500K, but this will be embedded into this embedding vector. They're not basically using the word embedding word2vec or globe, the dynamic learning, the embeddings, word embeddings, but still just really much smaller word embedding, as you learned. So for individual position, we'll calculate the self-attention. And for feed-forward network, this will be separate network. It will be separate network, but separate network, but they are the same. The weight will be the same. Weight within the same layer, the weight of this and weight of this will be the same, but within across different layers, the parameters are different. Parameter weights are different. Okay, let's go to self-attention. So self-attention means that for individual words in the input, we look at all the other words in the same input and how we can use that other words for encoding the current words. So in this example, there is a sentence: the animal didn't cross the street because it was too tired. So when it comes to the position of it, so we are computing the self-attention for it. So it's looking at all the relations, relevancy across all these words, and you can see there's more stronger attention to the animal than the street or tired or something, because basically the animal and it is representing the same object in this case. For representing or computing this, we make use of 3 matrices, and then the resulting vectors are also 3, right? They are key, query, value. So key is the basically current focus. and key will be the target where we are looking at, and so query is the current focus. For instance, it could be the query, and the rest of this could be key. And key and value are basically the same words. So, and query will be again, in this case, it will be it, and others will be the key. And the idea will be how we can compute the relevance between query, it, and the rest of the word, is street and animal and so on. And based on the relevance, we'll compute, multiply the relevance score with the value, so that we know which word we have to pay attention to more than other words. So in this case, the input will be only two words, thinking and machine. And let's say the embedding of those were like this, two vectors, like with size of 512. And then we have this weight matrices. This will be 5 and 12 times 64, 512, they are the same size. And the resulting key query value size of this will be what, right? There will be 64, right, for each. The key query value's dimension is 64. And the axis embedding size is 512 in the paper. And by learning this WQ, WK, WV, we will learn how to pay attention to particular word in the input from each other, right? So in the thinking machines case, since we start from thinking, this position from this will be query, and we'll look at the other words. If there's a thinking machine CEO as the third word, you will look at the relation between these words, right? So the current position is 0. From when we encode this, we'll have to look at other words, how much attention we have to pay attention, how much we have to look at the other words. So basically this represents the inner product between these two, all this. And n is the sequence, input sequence length. So in this case 2. But in the, as I mentioned, the original transformer model, the length will be 512 or 1024. The input token sequences. And if we compute this, this will be n by n. If n is 100, this will be 100 times 100 score matrix between query and key. And here we have scaling. Scaling happens in deep learning to adjust the values and make it not too big. And we kind of regulate the mean and distribution. And here in this case, the key vectors dimension is 64. Remember, a key query value, they are all 64. The dimension of them is 64. So we divide them by square root of 64. That's 8. The reason is when we kind of multiply this multiply these numbers, the mean value can be 0 when the original mean is 0 and the variance is 1. When we accumulate this, the mean of this could be 0 and the variance could be decay. There is a 64. So we try to not make this too big, and that's how this scaled up project came up. And then once we scale, then we make it as a distribution of the probability distribution using softmax value. So here we have a key query value and thinking and thinking. I mean, this is just thinking, looking at the original thinking and then relation between thinking. So itself, right, basically. And the score is 112 and it divided by 8, that becomes 14. And the machine case, the current focus is thinking, right? This is the query. And the relation between thinking and thinking, we computed, and thinking and machine. In this case, the query and key inner product is 96. We divide by 8 becomes 12. And if we compute the softmax between these two, we only have 2 words. So this will be more important. According to this calculation, this has more weight than the second one. The thinking is pay attention to itself than the other one, machine. If we have CEO, this will be computing more, this relation, and it should add up to 1 through softmax. So, as a result of this softmax, we will have this the original value. So we'll compute, multiply this into this, and multiply with this, and to create this Z score. This is Z score. And remember that the size of Z will be basically having 64 times 512. And if you can summarize the dimensions used in this calculation, this D model is 512, the size of the word embedding, and then the key query value size was DK, 64. And attention, when you compute the attention, basically this part and this part, we calculate this through this, and then this one, and the result of Z the dimension of this will be n times the sequence length times dk. Okay. And furthermore, we are not just computing this one time. We have a multi-head. So multiple times we do this, the same thing multiple times. And each time we'll have a different key query value weight matrices that we have to learn through training. And multiple attention mechanism. So in CNN, remember we had, if you know, that we have different filters to generate different features of the images. And here we'll have a different attention, and given the same input sentences, we can have also different view of the same sentence, and we can use those different informations. So basically, it creates more power to the modem. So original query key value, this will be 8 times. So from index 0 to 7, there are 8 of this. So attention head 0, 1 through 7. And calculate this attention separately for individual attention heads. So we can concatenate from, I'm sorry, this is 0 to 7, and altogether it will be 8. So size of this, because we are concatenating all of this, will be 8 times. 8 times of dk times n. And W0, the size of W0 will be of a multiple 8 times more. And through the multiplication, the size of Z remains the same. But we'll have to learn this weight matrix. So in one view, when we have a input sentence, in this case, there are only 2 words. We created word embedding for individual. This could be 500K. This becomes 512. 2 of them, and we applied the 8 attention heads, and they will need 3 of them each. And by the way, embedding, we use the same embedding for all of them. And we have all different query key value, and weight matrices are multiplied to generate the Z. Okay. So now we are looking at the positional encoding, the position of input tokens, how we represent this. So here there are 2 sentences. Although I did not get 95 in the last TOEFL, I could get in the PhD program. And second one says, although I did get 95 in the last TOEFL, I could not get in the PhD program. So if you look at these 2 sentences, the meaning of sentences is completely different based on the position of not, the word not, right? So the position has very important information for the same token. So we need to represent this somehow. So in the model, and what we desire is, first of all the positions, the positional information. I mean, for the first token, it should have a first token information. For the second token, we should know that this is the second token. The third one should be the third one should have its own positional information. So even if you change the input, that means if we have different sentence, the positional information for the first one should be same as the positional information for the second sentence, the first position of the second sentence. And the positional value should not be too large. If it's too large, remember the deep learning or multi-layer perceptron doesn't like large values. So we have to kind of keep it basically between 0 to 1. So positional encoding they used in the paper is sinusoidal. That's how we call it. Sinusoidal encoding is using sines and cosine functions, but it allows us to represent the order. So whether in this case not is in the 4th position or 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 for 11th position, there will be that should be different. The embedding of not is original embedding will be the same, but by having this positional information, the resulting vector will be different. So basically, we add this positional embedding into the original word embedding. And once we have this positional embedding, we can do the calculation for key query value vector, the product, and this will allows us to reason about the distance. So the function here, sine and cosine. So the position information will be basically this. In this case, du suis étudiant. The du's position is 0, suis étudiant. And this I will be the position in the word embedding. So in this case, the size of the word embedding is only 4. So this will be 0, 1, 2, 3, 0, 1, 2, 3, 0, 1, 2, 3. There will be the indices for I. So for instance, for this 0 position and 0i, this will be sine 0. And this will be a cosine 0. This basically 0, right? Oh, by the way, for the for the even positions, they use this one. For the odd position, this will be, they use this one, right? Position so this will be used for this and this, right? And this position information, the cosine information, will be used for this and this. So again, for when this cos is 0 and I is 0, this will basically sine 0 will be, if you remember, it's a sine function when it's a 0, right? So 0, when this value input is 0, the result will be 0. So it will be 0. For the position is 0 and I is 1, what will be the position embedding? We'll have to use this one, right? And since the cosine, no matter what the dividend is, the numerator will be 0, right? So cosine, you will have to look at this calculation. So anyway, I think if you try this, make this calculation, this will be more like this for individual one. 1, 0, 1, 2, 3, 2, 0, 1, 2, 3. If you place those in this equation, you can look at how the computation goes in there. Okay, so if you look at the patterns after these computations, it will be more like this. As the depth increase and the position, the depth means the embedding size, and then the position of the token, the 0 position and 1 position and 10th position, and the length of the input will, number of token could be 50. And the key thing will be we need to have a different values. Remember, we have to have the position representation, and then the value should be not too large, so it's becoming small. Sine and cosine, the range will be -1 to 1. So within that range, and we are able to represent the positions through this. So it should be all different for all POS value, II values. When they are different, they have the embedding value should be different. So now we have this positional residual connection and adenome. These are for improving learning, and in some sense we keep being able to keep the information, and also being kind of constraining the values not too big, and in some cases the distribution, in terms of distribution of the features, we regulate those values not too big, not too small. We'll see this, and the residual will have more connections. So in the input, the original input goes to the self-attention layer, but also to this layer. So there are multiple, basically, branches get to use in multiple ways. So we kept, while we are going through this, maybe we lose some information, but we can also directly connect to the original input. And there's normalization layer. Will regulate the features as the same mean and variance. We'll see a little bit later again. So residual connection, when we have input like x, again, it goes to some function, but also on the other hand, there is another way we can get the same information to, in some sense, it can keep the information. So it's a multi-attention input, but also multi-attention output. So this and this basically added here now. It's basically this, and the residual connection output will be like this. Layer normalization is used for stabilizing and speed up learning. So when the values, the variance and mean of some inputs too big or too small, it's not helpful for learning. So it's basically normalizing the inputs to the neuron. So you will, from the original value, you will take out the mean and divide it by variance. I mean, this is kind of a normal distribution basic equation. So here on the right hand, there's an example. If we have a popped and T stepped, there are two inputs, and we calculate the average of all this and the variance, and they are different from each other. So we basically calculate the mean and variance using, and then we assign the values to be more normalized into this. And this will stabilize the learning, not too big, not too small, and then speed up. So from this, we have this complete transformer architecture like this. We have encoding multiple layers, and the encoder input goes to the decoder side. So decoder side, also we have a residual connection and adenome, but we have one more input. The output sequence can look at, and when we generate the output, we need to use the encoder decoder attention. And so this is similar to multi-head attention, but the query is from this decoding part, and then key comes out from the encoder part, and key value matrices are from the encoder stack. Another difference will be in generating output in self-attention. We are currently generating output one at a time, so we can look at the past, but not the future. So the future, since we don't know yet while we are generating, we'll have a mask. So that prevents us to look at the future. And decoder, this animation shows the encoding. The 3 words come in, and then we have encoded information used for the decoding, and it generates one output, and then output is used for generating the next output. While we are generating, we look at still look at the encoding part. Right. So once we generate the first one, that information used for the next one. But remember, we cannot look at the future. The future is blocked when we look at only the past and the encoding part. And the final layer, since we generate one word, we'll use the one-hot encoding with the size of the whole vocabulary in English, like 500K. So it will decode the stack output. This will go to linear layer. They will change from 512 to 500K longer vectors. And then this is not probability yet. The numbers could be bigger and smaller in some sense. So we make a distribution, it's probability distribution, and through this, we'll pick the ones that has highest probability, get the index of the cell with the highest value. And the loss can be the difference between the correct output and the generated output. If the correct it matches exactly, then the loss will be 0, but usually it's not true. So we'll have to calculate the loss, and based on loss, we'll have to backpropagate to learning. And oftentimes when you generate the output, instead of the best one, we generate the best 2 or n, usually 2, top 2, and then use that to generate the output of the next step. Because in case we incorrectly generate the word in the previous step, we can still recover by having more than one result and keeping more than one results. So this is the model or architecture. We saw the paper, you can access through the archive. And this is not RNN based, but encoder decoder stack with the parallel mechanism focused on attention. And then it was able to use this architecture to train machine translation and generate very good results, a better result than before. Okay, this is the end of the slide. Okay, thank you.